So we've moved to talk a little bit about mass transport, and so what thought I would do today is kind of hit what I think are the high points from where we are with what we should have done so far. And so maybe I'll just do this. So the one thing that's slightly different when we're talking about mass transport from what we've done before is that instead of dealing with equations that include only a diffusive term, and so as you'll all know, that the system of expressions that we've been dealing with for the flow part have been things that look something like, in terms of the PDE anyway, something like this. In terms of terms that represent both the diffusive part and a capacitive part, if you like. And we've always been able to make those into an expression that looks something like, it's all on one side of the equation, a storage matrix, which operates on a time derivative of head, and this diffusive term on a conductance matrix, which operates on nodal values of head. And depending on whether we're looking at steady state, which is this part, or the full transient portion, which is this part, then we know how to solve those systems. If we look at advection behavior, advective behavior, then we have an extra term that is placed in here. And in terms of either, so this is fluid mass transport. And we've often referred to this as a diffusion equation. And so it is a diffusion equation, but the property that's diffused is the pressure. So it's not, the pressure pulse is what gets diffused in the system. It's not diffusion of the fluid per se, but it's diffusion of the pressure pulse in the system. And so this is definitely a diffusion equation. With that caveat, EQUN. And if we want to look at mass transport, which is when something is carried with the bulk motion of the fluid, because of course you could do conservation of mass where the mass is the fluid, and that is really what this equation represents. But if you're looking at mass transport when the mass is carried with the fluid, then the slightly different expression we have, so I'm just recapping from what you should already know, is that we define a concentration as a mass per unit volume that is mobile. There's a term that relates to advective flux and a concentration gradient in space, and that's equal to, sometimes this R term is 1 and sometimes it's not, but it represents a capacitance term, and so R is greater than equal to 1 and less than infinity. I think we haven't talked about that yet, but we'll talk about that today. And so here, this is again a diffusion equation, but it has an extra term, and this term is advection, as you know. And if we want to accommodate this, then we can straightforwardly do that, so long as we can write it in a form that's similar to this. Because we know how to solve this. We know how to solve this both for the steady case or for the transient case, which is the larger one. We know how to break them down into basically A times X equals B, just as a matrix to be able to solve them. And all that changes when we talk about mass transport is that we can now rewrite this expression as something that looks like a storage matrix times a constant rate of change of concentration plus a term which operates on the nodal values of the dependent variable, which in this case would be concentration, and is equal to a flux. And these individual terms end up representing, I think we've used the terminology of the diffusive matrix, which would be this term, or this component. This is diffusion or dispersion. And this is, in other words, K sub D. And the advective term, which is an extra term that gets added to it. And so these two terms get added together. And that in the past couple of weeks, you should now know that this advective term just has a form that we can define, just as in the same way that we've defined it for other kinds of conductance matrices or storage matrices. And it looks something like K sub A is equal to, I think it's an integral of the shape functions, transpose of the shape functions, velocities, the derivatives of the shape functions, dV. And so this is the shape functions, these are the derivatives of the shape functions in space, and this is the velocities that are applied somewhere within the individual element. And so long as we can define what this matrix is, then we can put together this larger combined matrix, and we can then solve it in the same way that we solve this, both steady state and transient. So that's the take-home message, I think, so far from what you've done. The extension of that, which I guess we probably will get today, is that we can also talk about heat transport. And that ends up being an equation which is largely similar to the mass transport equation. The conserved quantity instead of the mass of the solute, which is carried both by diffusion and by advection, is heat, thermal energy. And that thermal energy can either be conducted or it can be advected with the bulk flow of the motion, convected, advected. And that transport is acted against by, again, a capacitance term, which is really thermal inertia. That's why you have a big, heavy chimney in your house, to be able to absorb the fireplace so it kicks out heat once the fire's died down. And so if we write that out in terms of thermal conductivity, the dependent variable is temperature and how that varies in space. There's a component which is a term which is the velocity, again the advective velocity, change in temperature with location, and a capacitance term which is the density and the specific heat capacity multiplied by a rate of change of temperature with time. So this is specific heat capacity. This is thermal conductivity. And T is temperature. And so it's apparent from these that these expressions all line up with each other. This is the advective heat that's either carried through the system by a prescribed flow velocity or a flow velocity that develops maybe by buoyancy if it's natural convection rather than forced convection. And that all that changes in these is that you could write presumably an expression for this. The individual terms would be the same as each other, except now the dependent variable would be temperatures, and it would operate on both a diffusive or conductive flux and an advective flux, Ka. Again, nodal values of temperatures for each of these, and boundary condition fluxes, which are heat fluxes. And so they end up being identical to each other. So that's kind of closing the circle at least a little bit in terms of making the point that the reason that these finite element codes can deal with this multi-physics is that the equations start looking similar to each other. We also know that the forms of these individual expressions, so I was going to do this. Why won't it come back? Oh, there it is. I just changed color for the heck of it. Is that the term that operates on here is what we call zeroth order Pde, because it represents this term here, which is in time but not in space. This is the time derivative part. And we know that this matrix looks something like the products of the shape functions B transpose B over the volume as an integral. Always looks like this. We know that this diffusive term here always looks like an integral of the derivatives of the shape functions, A transpose dA dV. These are all submatrices. And so this is a second order Pde. In other words, this term here. So second order, zeroth order, and this is first order. And the first order one, it looks exactly like this. And so from this, you can see immediately that the variables in this, all you do is you change the dependent variable that you're monitoring. You change the coefficients that would go into these constituent matrices. So in other words, this constitutive matrix here would include thermal conductivity instead of diffusion coefficient, instead of hydraulic conductivity, Darcy's law. So this is Darcy's law, this is Fick's law, and this is Fourier's law. Just all the same. They define a flux driven by a gradient of temperature, concentration, or head or pressure, and are able to represent the constitutive matrix in this. This is just pre-multiplied by some coefficient, which would be specific storage or a retardation term, which we'll see today, or terms that represent the thermal inertia of the system, the capacitance, thermal capacitance of the system would go on this. And otherwise, these are just individual shape functions. We know that the integrals here just represent the volume of this element. It's really just defining the volume of the individual element that you have. And it's absolutely general as to whether you're looking at one or two or three-dimensional problems. And we should know, I guess, that the advective term is not particularly well behaved. And it's because of this velocity term. And there are a couple of features, I guess, of this matrix. By definition, this matrix has to be symmetric because it's a product of a transpose and a normal matrix, and a symmetric matrix in between. So by definition, this is always a symmetric elemental matrix and a global matrix that gets made out of those. This is almost anti-symmetric from the form that you've seen. And so it becomes more difficult to deal with numerically and also physically because of the stability of the system. And we spent a little bit of time mentioning that, I think. We've dealt with one-dimensional elements, and we've also dealt with triangular elements and what they would look like. And I think we've also dealt with how we can solve this in time. So that's kind of where we are with this. So what we'll try and do today is maybe close this out. And so the last things to deal with, I think, are one, to talk about the case when, in addition to this, in addition to the retardation term, which we can talk about, we can also talk about reactions in these systems, where you have species that instead of just being transported through the system, they actually might react with other components which are traveling with them, and how we would accommodate that in these sets of equations. And by extension, we'll talk about heat transport, because that relates also to the chemical reactions, because chemical reactions can be exothermic or endothermic. So there can be some heat that comes from them, or a heat sink that goes into them, and we can also accommodate that in a relatively straightforward way, so long as we're able to look at thermal transport in the system. So we're very close to being able to look at the kinds of behaviors that we kind of alluded to a little earlier in the semester. I don't know where it is in here. I don't want to lose my place. I guess I have to go two components back. No, don't do that. Come on. Yeah, and look at this. And so the idea is that when we look at these systems, if we look at the fluid transport system that we've dealt with, then we've really looked at terms which would reside somewhere here, a storage matrix and a conductance matrix. Go back, red again. When we've been talking about mass transport, we've been talking about a combined matrix which would operate on concentrations, and a storage term which would operate on rates of change of concentrations. And by inference, you could probably guess that when we talk about thermal transport, then we'll have a conductance matrix which would operate on temperatures, and again a storage matrix which would operate on the components that go into the term that represent capacitance. In each case here, when we're talking about advective behaviors, we'd have not only the conductive and diffusive term, but we'd have the advective terms added in here as well. But this is a convenient way for us to be able to think about this. It's convenient because I think what I'll try and do next time is, if we get finished with this today, is maybe we'll go through some examples and try and implement this where we have a system that actually couples itself to itself. I'm not sure how the connection is for ComSol in this room yet, but we can maybe try that next time. So we're almost in the position to be able to do that. Today, I think we will clean off looking at just this system of equations here, which is, oh, not that one, the one, yeah. The one that deals with contaminant transport, the one between these two lines. And then by inference, it's a very short jog to be able to think about heat transport that's added in there. So that's what I wanted to do today. And again, making the point that these all have similar structures. They all deal with a constitutive matrix, which is embedded in a conservation term, conserving either fluid mass or aqueous concentration or heat within the system, and being subjected to some appropriate boundary conditions. So they all satisfy the same requirements. So hopefully you've looked at some of the previous stuff, and we'll move ahead from that. So yes. So that's kind of a recap, a bit longer since it's been a while. But this is what we're attempting to deal with. So the new term today is that in addition to our behavior that we've talked about so far for now, we could also imagine that there's an extra term which allows us to take care of reactionary systems. So in other words, instead of being conservative, the systems we've talked about have been purely conservative. So what goes into the aqueous solution remains in there. It doesn't get taken out onto the solid, and therefore it's always present in the aqueous mass that's transporting its way through the system. But you could imagine a case where you'd have reactions with particles that it's flowing past, and there's material that's either dissolved or precipitated, or indeed there could be components within the flow field which react with each other to create new aqueous compounds as it travels downstream. And so those behaviors come under the guise of sorption in terms of being able to remove components onto the solid, and first-order reactions and multiple reactions in terms of being able to look at individual reactions. So for us, first-order reactions would be things like precipitation and dissolution, which are driven by the concentration gradients between the static media which you absorb onto and the fluid that's flowing past it. And multiple reactions would be actual reactions that occur within the flow field. And they're relatively straightforward to take care of. We'll come back to this as the third of these, this suite of behaviors. And so this is kind of a discussion, or a discussion of those three types. I'm not sure we need to spend much time on it rather than just to move straight away to talk about them. So kind of one way to deal with reactive behavior is to use sorption as a behavior that represents retardation. And sorption just means that a portion that is carried in the flowing fluid is removed and put onto the substrate, which is then no longer in the flow field. First order reaction would be where you take something such as quartz or silica, which is present statically within the sandstone that you're flowing past, and you dissolve a portion of that into the flow field and carry it downstream. And when concentrations change as you get further downstream, you could either dissolve more material from the substrate, or if it gets high enough saturation relative to an equilibrium saturation, it deposits itself onto the material that's flowing past. And the most complex of them would be to deal with these multiple reactions, which is the last one we'll deal with. So let's just talk about each of well, take them in sequence and talk about what each of them are. So if we look at retardation or sorption is just the approach where we have a conservative relationship, which is all the terms that exist within this box here, which we've talked about, but where we have an additional term that you could imagine that would represent a source or a sink. Because each of these terms have to be added to each other, they all have to have the same units. The units has to be, concentration units is a mass per unit volume, and it's changing as a function of time, not temperature. Maybe I'll write it as T rather than temperature. And so this is a mass rate per unit volume per unit time. It's one way to think about it. And so it's the amount of mass that you're accumulating in a given volume in a given time. And so it's really the units of a source or a sink. And so what you could think about this is that if you're removing stuff from the flow field that's no longer mobile to move in the flow field and attaching it onto a static substrate that the water is flowing past, then you can think of that as being a sink from the flow field into the solid which gets lost. And so one way to think about that is to define it in terms of a sink. This is a sink. Oops. Or a source. If it comes from the substrate into the fluid, then it's a source. If it goes the other way, it's a sink. And just in terms of the terminology that's used, it's often defined in terms of a rate of concentration change C star, which is concentration on the mineral surface. And by convention, it's conditioned relative to the bulk density of the porous medium. So if this would be a rock, it'd be 2,500 kilograms per cubic meter, and this would be the porosity of the material it's going through. But the important term is this rate of change. So this is a rate of change of concentration, dc dt, that goes onto the solid. And since the rest of the equation is written in terms of concentration within the fluid phase, then what we need to do is have something link the amount that gets taken from the fluid and put onto the solid, which we could perhaps measure, and relate it to the concentration in the fluid field. And so we do that in terms of an isotherm. And an isotherm does this. You take a beaker full of sand, and you put fluid with some concentration in it, and you allow it to reach some equilibrium concentration, that the concentration that puts itself on the grains of the sand will be in equilibrium with the concentration in the fluid. They won't be the same, but they'll be in equilibrium. And if you measure that concentration that's on the sand, you'd have a number and you'd have a point. If you double the concentration in the fluid and measure the concentration on the solid, you'd have another point, and you could create from that a so-called isotherm. And an isotherm is merely something that allows you to relate a concentration on the in the fluid relative to the concentration on the solid. And in other words, you can define that by the gradient of this line, and I guess the gradient of the line would be what? It would be change in concentration in the fluid relative to the change in the concentration on the solid, which would just be the wings of this triangle, and I guess this would be equal to 1 over the distribution coefficient, which is this value kd. And so in other words, it's an experimentally determined fit. You know what kd is, and so you can figure this out in terms of the rates of changes of concentrations on both the aqueous component and also the solid component. And so what you could do is you could take this expression here and you could modify it by multiplying this term here by just 1 over 1, which is dc/dc. And if that's the case, then you can immediately see that the value of dc/dc star, this term here, is exactly this relationship, well, the reciprocal of it. And so that's equal to kd, the reciprocal of this. And so as a convenience, we can transform it, instead of being related to this concentration on the solid, which all of a sudden is a new variable in this equation, to the concentration in the liquid, which is related to the concentration in the solid through this equilibrium isotherm. And so we can substitute into this, and we end up with an expression that includes this kd term. So that's the first part. The other part is that now we realize that with this term, so what's this term is just going to be substituted as, this is so this term on the left-hand side is going to be minus rho over porosity. dc/dt is going to be equal to kd times dc/dt. So that's what this term will look like. And so our reason for writing it that way is that now we realize that we have a term that represents capacitance, and we have a new term that represents a capacitance but in a different way. And so if we can take this to the left-hand side, then we end up with a new expression which includes this so-called retardation effect. And so if we manipulate it that way, we still have a single partial differential equation. It's written only in terms of one dependent variable, which is concentration in the fluid. We don't have to worry about concentration in the solid. We're making an assumption that there's always an equilibrium between the concentration in the fluid and the solid that it's flowing past. That's an implicit assumption. And we have a new term on the left-hand side that, instead of being just 1, is equal to 1 plus something. Something that's always bigger than 1. It can be 0 or bigger than 1. So this term in its ensemble will always be 1 or larger. And so we can think of this as R, which is this term here, so-called retardation coefficient. And the reason it's referred to as retardation coefficient is because it represents the physical behavior. It's the same as the chromatographic effect. If you take a piece of paper, blotting paper or filter paper, and put an ink drop in water, and then dip it into water, you'll see it climb up the paper by capillary action, but you'll also see these chromatographic fringes develop depending on how far or how quickly the dye from the ink is able to travel up along this chromatographic paper. And so the physical meaning of the retardation coefficient is if you divide both sides here by r, this term on the left-hand side all of a sudden becomes r over r, which is 1, of course. And these terms, which originally were diffusion, dispersion, and advective velocity, just become divided by r as well. And so it's useful to think physically about what that means. And physically what it means is if you take a core and you looked at transport along that core, or an aquifer for that matter, then if based on the velocity field, the water flowing through here at some advective velocity v sub a, and I'm not sure whether we've talked about it before, but the advective velocity is equal to the Darcy velocity divided by porosity. Darcy velocity is a bulk flow. Advective velocity is the time it takes for a molecule to go from the upstream to the downstream, so it's important to make that distinction. But since velocity is equal to length over time, all right, lowercase, then the length traveled in a given time is just going to be equal to the advective velocity multiplied by that time. And so if we want to calculate how far a pulse would travel downstream, you can get it very straightforwardly. If you know what the advective velocity is, and you know how long it's been traveling, it's just like traveling in a car basically, that it would be such and such a distance downstream. The net effect of having retardation is that you are effectively reducing the transport velocity by that retardation factor. So if it's 1, then there's no change. If the retardation factor is 2 or 10, which it might be for many solutes in groundwater, then you reduce the velocity by a factor of 2 or a factor of 10. And so there are two effects that are important. One is that you will retard the rate of transport of this, hence its name. So in other words, the length traveled would actually be equal to the effective advective velocity, which is really the advective velocity divided by the retardation coefficient, and also multiplied by how long it's been traveling. So all we're changing it is to accommodate the fact that, so this is the Darcy velocity, this term divided by porosity is the advective velocity, and so this is the advective velocity divided by retardation coefficient. And so there are two features. One is that this isn't actually always true, but it's true enough for us to make it a golden rule in this class, is that it will travel less far. So if the retardation factor is 1, it would have gone this far. If it's 2, it would have traveled half as far. If it was 4, it would travel just quarter as far. So that's the one parameter, which I guess is this. And the other feature is referred to as self-sharpening. And so what that refers to is that if this is the part that defines the advective transport downstream, then this defines the spreading. And so if, for instance, the diffusion term was 0, if we imagine, then there would be no diffusion. If that were the case, then the front that would come down here would actually be a plug flow. And so if you looked at it in the core, it would just be a sharp front. Ahead of it, there'd be pure water. Behind of it would be concentration at the concentration of the upstream boundary condition is, and it would be just a vertical line. If diffusion is non-zero, then it would be dispersed about that central point. Not exactly, which means that ahead of the front there is actually some concentration. So in other words, even though it hasn't arrived here, because some of the paths in getting to you have been fast paths where this finger of solute has arrived maybe earlier, then the concentration has arrived earlier upstream of where we are. And likewise, because it's being transported ahead of the front, there's also parts behind the front where the fingers haven't gone and it's actually pristine fluid behind that overall front. But the self-sharpening nature of it is apparent from this, is if you take this behavior to represent, if this is 0, it's sharp, and if it's greater than 0, it's less sharp and gets progressively less sharp as this value increases, then as you apply a retardation coefficient to this, then it physically makes this a smaller number. And so it makes this front that would be the retarded front actually sharper than it would be otherwise. Cigarette smoke. So interesting. At very low concentration, essentially. What we can pick up at very low concentrations. So those are the two features. One, it travels less far, and two, it self-sharpens. And so if you wanted to implement this, I think you can probably see straight away that if you wanted to implement it in terms of the relationships that we talked about now, I guess it's this term here, isn't it? In terms of this, then all that would happen is that the coefficient that we use to multiply the dc dt term by, instead of being 1, is some other number. It's 2 or it's 10 or whatever. And so in other words, it would merely be a multiplier on this particular relationship here that we'd have to apply. So it's not very difficult to be able to see how we would do that. And so we won't really say any more about that. So that's the first of our three ways of dealing with things in progressive order of complexity, I suppose. First is by taking care of sorption. And that's what we've talked about, which is physically manifest in terms of being a retarded transport. The second one is in terms of a single component and looking at transport of a single component with dissolution or precipitation reactions included. So I seem to have a predilection for red for some reason. And so it could be something like this, where you have silica plus water becomes the aqueous form of silica, and it's dissolved in the flow regime. And so one way in terms of being able to take care of that is again to deal with the idea that the units that define this behavior are mass per unit volume per unit time. So it's a mass rate per unit volume. And so we can think of this as a sink or a source. And so the other term that we could add onto this in terms of being the sink that we defined in terms of sorption would be just to add it as a reaction. And so a reaction, again, would be a rate of change of mass per unit volume per unit time. Rxn is just a shorthand for reaction. And so if we add this reaction term to the right-hand side of our equation, then we need to be able to relate that to something. If we think that the rate at which we change concentrations within the aqueous phase is related to a difference between the aqueous concentration relative to an equilibrium concentration times some coefficient, then it's physically saying that if the equilibrium concentration at which no material gets either dissolved or precipitated on the substrate, on the particles, if the concentration of the water is exactly the same as that, there is no change, right? There's no motion, there's no impetus to be able to either dissolve or to precipitate. If the concentration within the aqueous solution is larger than the equilibrium concentration, then it would precipitate onto the static stage. If the concentration in the water was lower, then we'd net dissolve stuff from the static stage into the water, and we'd raise the concentration if it was static. And so that's really all this is saying. And it's saying that we can calculate or define a rate at which that happens as a function of the imbalance. As the imbalance between these gets larger, then the transfer rate between aqueous and solid increases proportionally to that magnitude. That's all. And so it may be that this is a single value, or maybe it's a different value for dissolution versus precipitation. It's certainly easy to accommodate that. If we take this and we add this onto this expression, we end up with this. And then our task then is to figure out how exactly we write the finite element equations that would define that behavior. And so that's really what this next statement is basically doing. We know what the finite element equations look like if we deal with this normal equation, I think. And I suppose we could look at them. They're written out here. The capacitance term is this term here. So if I number them 1, the diffusive term is this term here. Yeah, okay. Written slightly differently, right? But with this term taken out, A transpose A. And the advective term for the first order components is the one that we talked about earlier on today. So those are the 3 parts that represent this. There's a flux term, which is always present in this, if we want to be able to write it. So this is what we've referred to before as K diffusive underscore. This is what we've called K advective underscored. And this is the storage term. So these are the terms you've had before. You remember storage times concentration gradient plus the diffusive term plus the advective term together operating on nodal concentrations equals Q, just to remind ourselves, right? This is this equation. This is the first term. This is the second term, and this is the third term. And this is what comes out of when we play around with the transform the partial differential equation into a finite element statement. We end up with this extra term, which represents the sources. So what we need to do is be able to figure out exactly what this would look like. And we can do it just by heuristics, if you like. This is a zeroth order term in space, right? Just like this. This is second order. This is first order in space, but this term is zeroth order, just like this. So we can surmise from that this term, which we're, by the way, replacing with 2 components, is going to look something like the storage term, which is going to be equal to an integral, the shape functions, and the volume. If we have to multiply it by some other terms, these are the terms we have to multiply it by. And so I guess it would also be multiplied by this lowercase k and the difference between the concentration in the aqueous phase and the equilibrium concentration, EQ. As a product, this is multiplied by in a matrix way. X is times. And so this is a constant, and these would be vectors or nodal values of concentrations either in terms of the equilibrium concentration or in terms of the aqueous concentration of that component. And so really all that we need to do is add in another term, which is going to look like this, and will look like this. And so that's this term here. So it's zeroth order. So this is this term here, right? This kind of storage matrix as we've called it before. But it's operating on a parameter. This is a dissolution coefficient or precipitation coefficient. We could figure out exactly what the units of that are if we wanted to, I suppose. Since this is a concentration and this is a concentration, the units of this have to be in units of 1 over time, right, to be consistent with this, just as it turns out. And nodal values of concentrations and a coefficient. And so in the same way that when we now want to solve it, to be able to solve this in time, we know that we can only solve equations if we write them as we can only solve them if we write them as KC equals Q, would be our way, right? or AX equals B, however you want to write it. So we have to manipulate it in some way to get it in this form. And our way of doing that is to basically take this term, which we've kind of defined, and to write it overall in this matrix form. So this is, let me change colors just because I can. Apparently I only like red and blue for some reason. This is this term here. This is this term here. The Roman 2 is for second order Pde, which is what this is. And I guess, you know, if we follow this down through here, this is all vertically compatible, I guess. This is this term here. K1 is for this. And this final term is this. This is zeroth order, so it's exactly the same relationship as we had here. And so now we want to be able to transform this matrix equation. We know this coefficient, we know this form is this B transpose B part. These are just vectors of the concentrations at the nodes in terms of the aqueous concentration and some other constant, which would probably is just a single number. And now we need to rearrange it to get it to solve it in time. And so to solve it in time, we need to do what we've done before, and we need to look at the parts which we don't know. And so if the easiest way to do that is you remember that C dot is equal to 1 over delta time multiplied by the concentration at time t plus delta t minus the concentration at time t, if you remember that. These are just the two vectors from the two time steps. And so if we want to substitute this into this expression here, and if we want to also substitute it into this expression here, which are the two places it will go, then you know that we want to keep on the left-hand side of this equation all the terms that we don't know, which would be this. And we move to the right-hand side all the terms that we do know, which would be this. The concentration at the previous time step, which I guess we know. And that's all that's been done here. So you'll see what we've done is we substituted for this term here. We have 1 over delta t times the concentration at the new time step. So this is the 1 over delta t. This is the concentration at the new time step, which is the same one that operates on all of these other terms here. And we've taken the other part of this over to the right-hand side, where it exists here. 1 over delta t multiplied by this coefficient and multiplied by the value that we know from the previous time step. So this is the part that has come from here, if you like, is this one. And the other term that we have would be, let's see if you follow this arrow across here, the other term here, which is again the concentration, same concentration that we've moved across from here. We've kept 1 on one side, which is this term, which represents this. And the one we've moved to the other side is this term here, which is the second part of this time derivative, dc dt. And so now what we have, we know absolutely everything on the left-hand side. This is a matrix we can put together. K0, K1, sorry, K2 and K1 are things we know. These are all parameters we know. The only thing we don't know is this. And everything on the right-hand side we know absolutely, because we've solved for the previous time step. And so we can solve from that. And so that allows us to be able to march in time in the same way. So that would allow us to be able to figure out exactly what's dissolving off the material and getting carried downstream, and whether it might precipitate downstream when the concentrations, I guess it'd go the other way. It would dissolve even more as its concentration reduced as you went downstream. Okay, so that's the second of the things that we're going to talk about. So we said we'd talk about sorption, which is the first one, which is this retardation approach. We said we'd talk about first order reactions in terms of just dissolution precipitation, which is what we've just talked about. And then the much more general behavior is where we talk about reacting solutes. And so that's the more difficult one to talk about. It's kind of explained here. So this is maybe the most complex of these. And so the idea is that you have stuff, for some reason it's at the beginning of these notes rather than the end of the notes, and this is the easiest way to deal with it in this order. So we know that if we have components that are in the aqueous phase, they can react with each other. Reactions will progress within a beaker at some rate depending on kinetics. But if we ignore the kinetics and we think that the reactions occur quickly and get to equilibrium much faster than they travel downstream, then we can use the idea of equilibrium reactions and look only at the equilibrium state. And that's really all we'll talk about in this class. And so the idea is that we can write our advection diffusion equation in terms of a given solute. And so we could have one component. We could have sodium. We could have chloride, as in salts, moving downstream. Those would be two. And so we could write, if they were being transported independently, two equations, each representing the concentration of one species. If you have 10 species, you have 10 equations. They don't interact with each other on their own, except through this term, which is this reaction coefficient on the right-hand side. So you'll notice this as the capacitance term, this is the advection term, and this is the diffusion or dispersion term, and a reaction term on the right-hand side, just written a little bit differently from what we've had before. And so what we could do is we could look at this kind of straightforward reaction where you have two reactants forming one product, and there is a forward reaction rate, the rate at which you create C from A and B, and a backwards reaction rate, the rate at which you create A and B out of C. And we'll only look at the case where the rate at which one is being produced relative to the other is exactly the same rate, in other words, the equilibrium rate. And we can define the rate at which you can define the forward reaction in creating C as some reaction rate coefficient K1, which is this top term here. And the reverse rate at which you create A and B from C is this term here. We can define what these terms are. If we look only at the equilibrium condition, then these two have to be equal to each other. You're making one as quickly as you're destroying the other one. And so if that's the case, we can equate the two parts of equation 3 to each other, which is really what equation 4 is. And if we rearrange them, you end up with a rearranged equation where we define, this is saying that the concentrations of A and the concentration of B multiplied by each other, multiplied by this rate coefficient, gives you the rate at which you create this other component. And the rate at which we're creating A and B from C is the concentration of C multiplied by this rate coefficient. And so if we rearrange 4 into 5, then at equilibrium, the concentrations of these are given by the ratio of these two rate coefficients. So our interest is in being able to represent a pretty complex system where this stuff is traveling both downstream and reacting with itself and creating new products. And one way to think about that, a useful way to think about it, is that you could have this reaction going on in a beaker, and the reactants would be reaching some kind of equilibrium, or would have reached equilibrium, but are also being physically moved from one location to another, which is the transport process, which we will accommodate in this particular relationship here. And so the reaction part is what's going on in the beaker, and the transport part is carrying the beaker downstream. I think it's a useful way to think about it. I really like red for some reason, so I'll go back. So imagine that you have these reactants within a beaker, and depending on what you have on your notes, this may be a 1 or a 10. They could be switched. This is switched, so it's actually correct. So you have 1 mole of each of A and B in the system. Of course, 1 mole of A and B will react with 1 mole of C. We'll create 1 mole of C, I guess, just from the straightforward reaction. So what we can do is if we have 1 mole each of A and B, and if we look at the amount that we have of C, if we put the concentration of C as equal to what we'll call X moles of C, then since C has to actually originate from the two reactants, of which there are 1 mole each, then the amount of C that we can have is going to be X, but that's derived from 1 mole for which A has to equal 1 mole minus the amount of C that's produced, which is 1 minus X. 1 mole minus the number of moles of C. And also this reactant B has to be equal to the same, because they're stoichiometrically, I guess, they're equivalent to each other in this reaction. 1 plus 1 of these equals 1 of these. And so this is the amount, X is the amount of C. And so if you look at this relationship here and you divide both sides through by C, you end up with this expression here, right? And this has to be equal to K2 over K1, just by rearranging this, right? So divide both sides by C and you get this expression here. And if you look at replacing each of these with the concentrations, the concentration of C is X, the concentration of A is 1 minus X, concentration of B is 1 minus X, and so this has to be the ratio of the concentrations of C that are present within the system. And so we can, if we start off with 1 mole of A and 1 mole of B, and we know the reaction rate coefficients, we can calculate how much of the product we get out of this, which is X, which we'd like to find out. And you can solve the quadratic, but if you solve it, I think it terms the solution is here. I think it has to be, if this is so 1 minus X has to be equal, since this is 1 over 10, 1 minus X all squared has to equal 0.839. I'm just doing this by looking at the results. So in other words, if 1 minus X squared is 0.839 and the value of X is 0.0839, then this ratio really is 10 to 1. And so this actually is the solution. So the solution for this has to be that X is equal to 0.0839. And if that's the case, if we know the amount of C we have, by definition, the amount of A we have is 1 minus C, and the amount of B we have is 1 minus C also. And so we have that. And so we should be able to calculate exactly the amount that we have at equilibrium. And it's a single amount. It doesn't mean the reaction has stopped. It just means that the same amount is reacting in the forward direction as in the reverse direction, and therefore the masses of the two don't change. So that's one way that we could check what the results would be in our beaker. So if we want to now deal with that, so we have a beaker that contains this and is traveling downstream and moving through our system, then what we could do is we could write a single expression to represent that. And so we'd write this equation for species concentration of A, which we've called, I guess we just did this bracketed term, this means the concentration of A. We'd write an equation for the concentration of B. And we would also write an equation for the concentration of C, which would be this. And so what we'd have would be 3 equations for this. It turns out that we actually don't need the second one. The reason we don't need the second one is because A has to be equal B. A and B are the same. And so we actually only need two equations to deal with. We could get rid of one of them. And so we'd have two equations like this. They're completely separate from each other, except one is written for A and one is written for C. And the only way in which they interact is through this term here, this reaction rate coefficient. And this reaction rate coefficient is given at every single point within our system by this term here. And so in other words, this would be in the first equation. And so we take the value of concentration C sub A, we'd multiply it by the concentration of C sub B, which is actually C sub A itself. And we'd also look at the concentration of C, and we'd calculate a source or sink term, which would go into this part. And so basically this is saying that within this beaker, a certain amount of this material is being taken out of A and put into C, and vice versa. I guess it's really only one way. It's a net zero. Yeah, it's there's really only one change. What comes out of A and B has to go into C. It's the only place it can go. And so we have a relationship which represents the behavior for the sink or source that goes into the first equation, which is here. And we'd have a sink or source that counteracts with that goes into the third equation. And the second equation doesn't exist because A and B are the same as each other. So that's it. And so if you look at writing that out, when you have multiple components of this, it's just this product term, but that's basically what we're attempting to do. And so all it does is it acts as a sink or a source that removes material from one conservation equation into the other, and works that way. So the other interesting thing that relates this, or it should all be interesting of course, but the other interesting thing is that this doesn't necessarily happen isothermally. And so when you get reactions that are exothermic, that create heat, or that are endothermic, that require heat and therefore cool their surroundings, then that may be something you also want to accommodate. And the one way to deal with that is to deal with this so-called heats of reaction. And so related to these reaction rates are that if you know what the heat of reaction is for that particular reaction, so this is known, for, I guess it would be exo or endothermic reactions. So delta H is some specific heat of reaction, specific heat of reaction. And if you multiply it by how vigorous the reaction is, how much is changing over, the reaction rate, which we would get from these values here. So in other words, these values, the generalization of these values is this expression, and this expression is what goes in here. Then all of a sudden, this represents a heat source. Or a sink. So in other words, if it's an endothermic reaction, then it's creating heat, and therefore it would supply heat to the fluid that it's traveling in, or the porous media that's traveling in. And if it's an endothermic reaction, it would chill the surrounding component. And so this can be put in, so this heat source or sink can be applied to the porous medium or the fluid in which it sits to actually chill it. And so the way that would work is it would work on another relationship which we would define to represent heat transport. And you remember when we started off on this journey this afternoon, we had this expression here. We made the comment that if you look at mass transport, we have a diffusion advection equation that transports mass concentration. If you look at the heat transport term, you have a conduction advection equation, conduction term, advection equation, and a capacitance equation that looks at the heat flow in the system. And so what we could do, since this is basically a source or sink term that exists here, we could add that flux into that equation. And so if you look at this expression here at the bottom of the page, and if I blow it up, then this expression here is exactly the heat flow equation that we alluded to before. So what is this? This is lambda d2t dx squared. Thermal coefficient. Fourier's law is that heat flux is equal to thermal conductivity times change in temperature with location. A minus sign because it goes in the opposite direction of the positive gradient. So that's this term here. This is thermal conductivity. This is the part which is advective velocity multiplied by rate of change of temperature with location. This is density and specific heat capacity times rate of change of temperature with time. Zeroth order, second order, first, I guess we better do it this way. Zeroth order in space, first order in time, first order in space, second order in space, and this is this heat sink. So this is a sink source. And so now this is the term that we can calculate. If it's a vigorous reaction, the reaction rate that we get from here from these relative concentrations is a big number. A lot is changing from one material to another. Therefore, it's creating proportionately more heat if it's vigorous or less heat if it's less vigorous. And that defines the vigor of this, a coefficient, and therefore the amount of heat exchanged here. This goes into this term for the PDE. And again, if we summed up, I guess we should make it clear that we want to sum up all the specific heats of reaction that we get from all of these reactions. From reaction 1, for the reaction A, and also B, and also C in this particular case, all of those components would go in here, and it would either add heat to the system or subtract heat from the system. And so that's kind of where we needed to be able to start now looking at the multiphysics of these systems. If we roll it back now to where we started off at the beginning of class today, at the beginning of, I think, 3.1, which was right before this, I think, then hopefully you see exactly where we are. And so we now know how to be able to create these individual systems of equations as finite element equations, and that's exactly what COMSOL does. They exist on their own in these individual rows. So right as we have these, they don't talk to each other at all. So this would be concentrations within the system, rates of changes of concentrations, and mass rates of supply to the system due to reactions in this particular case. We wouldn't just have a single degree of freedom per node for concentration 1, but we'd have concentration 1 and concentration 2 and concentration 3 for A, B, and C for our cases. So we'd have 3 of these particular concentration equations to represent it. So you could imagine that if we, for instance, had a triangular element, then the degrees of freedom at each of these nodes would be what? We'd have concentration for species A, we'd have a concentration for B. We've said those are the same, so we could probably get away with getting rid of one of those. And we'd have a concentration for the products. So these are reactants, these are products. So we'd have 3 concentrations that go in here. If we were driving this thing by flow, in other words, we wanted to calculate what the flow velocity was in here because that represents the advection term, then we know the flow velocity is equal to permeability divided by viscosity multiplied by change in pressure with location. Or if we write it in terms of heads, which is really what we've been doing, we could write it in terms of k times dH dx. So in other words, we'd also have a value for a nodal value of head, because the change in head from node to node would describe the gradient, and from that gradient we could calculate what this velocity is, and this velocity is something that goes into this advection part of this equation. So we'd have 3 nodal variables for concentration, we'd have 1 nodal variable for head, and if we wanted to deal with the temperature term, we'd also have a nodal value for temperature. And so we could solve that equation. If we put those equations together without linking them to each other, then they'd act absolutely in isolation from each other. But our desire is to be able to make them talk to each other, so that, for instance, the heats of reaction that come out of this reaction between these creates a heat source which gets fed into this. And so our way of doing this is to be able to calculate what the heats of reaction are from the way that we talked about it, and to have it put into this equation here through a heat source term on the right hand side. And so that's really how this linkage works. And so we're now at the stage where we can actually do something maybe a little bit interesting with this in terms of linking these together. And maybe we'll try that. Yeah, why don't we try that next time? I'll work on a little example for next time. So you'll notice that still we've only talked about scalar values. They have magnitude but not direction. Concentrations have magnitudes, heads have magnitudes, temperature have magnitudes, but they're not like stresses or velocities where they have both magnitude and direction. And so even though we have more than one of these values, one of these degrees of freedom per node, they're only still scalar values rather than vectoral quantities. And so that's kind of the end of where we are with this. We've talked about fluid transport, mass transport, and in the last 10 minutes, heat transport. They're all scalar values. All the other systems that we'd like to deal with now are vectoral quantities. And so in a little while, we'll talk about fluid flow, not in terms of Darcy fluid flow, but Navier-Stokes flow, where we have momentum for the fluid that we have to deal with. And we'll deal with that only very briefly. And then we'll talk about solid mechanics, where we have deformation in porous media, which get factored into this. And that, as you can see, if you're waiting for the punchline, that would be a stiffness matrix, which would go here. And it would be a nothing matrix that would go here. It would be a stiffness matrix that would go here. If you remember back to when we started talking about this, all of the finite element methods were developed for solving solid mechanics problems. So this was the genesis of the method in itself, even though we've concentrated maybe on a reverse historic look at using the relatively simpler systems to deal with it. But so I think where we are now is we have enough under our belts to be able to say something about how we might couple these systems to do it, and maybe we should actually try doing that in class next time. Okay.